All right, today we are diving into one of the biggest, most important ideas in all of chemistry, the mole. And yeah, it might sound like a tiny little thing, but trust me, its impact is absolutely huge.
So, let's just start with a basic question. I mean, we all know the universe is built from atoms and molecules, right? And there are just countless trillions of them in the tiniest little thing you can imagine. So how in the world do you count them? You can't just line them up. Well, this is the exact puzzle that chemists had to solve, and their solution is nothing short of brilliant.
To get our heads around this, we need a way to talk about massive amounts of impossibly small things. So chemists came up with a concept you can kind of think of as the chemist's dozen.
Think about it like this. When you hear a dozen donuts, you instantly know that's 12. Dozen is just a simple word for a number. The mole is the exact same idea. It's just a word for a number. The only catch is that this number is, well, it's ridiculously huge, because atoms are ridiculously small.
And just so we're all on the same page, let's get this out of the way. No, we are not talking about the fuzzy little creature that digs holes in the yard. In chemistry, a mole is just a number. It's a unit for measuring an amount, and really getting a feel for it is the key that unlocks pretty much everything else.
So what is this special number? It's got a pretty cool name, Avogadro's constant. You'll often see it written as a capital N with a little subscript A. This is one of the fundamental constants of the universe, and it officially defines how many things, atoms, molecules, whatever, are packed into one single mole of a substance.
And there it is, 6.02 times 10 to the power of 23. That's a 602 with 21 zeros tacked on the end. It's a number so big our brains can't really even picture it. But that's the magic number. It doesn't matter if it's a mole of carbon, a mole of water, or a mole of bowling balls. It's always that many.
Okay, so why that number? Why is just specific, gigantic number? Well, because the mole's real job isn't just counting. Its true power is that it acts as a bridge. It perfectly connects the invisible, microscopic world of atoms to the macroscopic world of our labs, the world where we can actually weigh things out in grams.
Now, to understand this bridge, we got to get three quick terms straight. First, you have atomic mass. That's just the weight of one single atom. Then you have molecular mass, which is just all the atomic masses in a molecule added together. But the real star of the show is molar mass. That's the mass in grams of one whole mole of something. And here's the magic trick. An element's molar mass in grams is the same number as its atomic mass. That's the bridge right there.
And believe me, this concept is a really big deal. The mole is one of the 7 official SI base units. That's the international system that scientists all over the world use for measurements. It's right up there with the meter, the kilogram, and the second. It really is a cornerstone of all science.
So how do we figure out the molar mass for any chemical out there? It's actually really straightforward, almost like following a simple recipe. Step 1, you look at the formula and see what elements you're working with. Step 2, you grab your trusty periodic table and find the atomic mass for each of them. Step 3, you multiply that mass by how many atoms of that element you have. And finally, step 4, you just add it all together. That's it.
Let's run through a quick example. Sulfuric acid, H2SO4. Following our steps, we see we've got hydrogen, sulfur, and oxygen. The formula tells us there are 2 hydrogens, 1 sulfur, and 4 oxygens. We look up their masses on the periodic table, do the multiplication for each one, and then we just add up that last column. Boom, 98.09 grams per mole. That means if you go into a lab and weigh out exactly 98.09 grams of sulfuric acid, you are holding exactly 1 mole of its molecules.
Okay, so we've got the concept, we've got the calculation. Now let's see how this is actually used. This is where the mole becomes this incredibly powerful tool, letting us switch back and forth between mass, moles, and the actual number of particles.
Let's just walk through a classic problem to see how this plays out in the real world. We'll take it step by step so you can really see how chemists use this bridge to get from what they can measure to what they want to know.
Okay, here we go. The molar mass of neon is 20 grams per mole. So,
how many actual atoms of neon are there in a little 2.5-gram sample?
This is your classic two-step process. First, we have to get from grams to moles, then we can go from moles to the number of atoms. So we take the mass of our sample, 2.5 grams, and we divide it by the mass of 1 mole, 20 grams. That gives us 0.125 moles. Okay, now that we know how many moles we have, we just multiply that by Avogadro's number to get our final answer. And look at that! That tiny 2.5-gram sample has over 75 sextillion atoms in it. Wild. Let's try another one. But let's go the other way this time. Here, someone has already counted the molecules of oxygen for us. We have a gas cylinder with a specific number of O2 molecules. We need to figure out, first, how many moles that is, and second, how much that gas actually weighs. So for part A, to get from the number of molecules back to moles, we just do the reverse of what we did before. We divide our particle count by Avogadro's constant. Simple enough. That gives us about 2.5 moles. Now for part B, we need the mass. But, and this is a really important detail, we're dealing with oxygen molecules, O2, not single atoms. So we first have to find the molar mass of O2, which means we take oxygen's atomic mass and double it. That's 32 grams per mole. Then we just multiply the moles we found by that molar mass, giving us our final answer, 80.3 grams. All right, last one. Let's look at nitrogen. This problem has two pretty cool parts. First, we're going to use the mole to figure out the absolutely minuscule mass of a single nitrogen atom. Then we'll go back to a more familiar calculation, finding the number of nitrogen molecules, N2, in a big 290-gram sample.
Okay, let's break it down. Part A is just awesome. To find the mass of one single atom, we take the mass of a whole mole of them, that's 14 grams, and we divide it by how many atoms are in that mole, Avogadro's number, and you get this unbelievably tiny number. For part B, we're back in our comfort zone. But again, you have to watch the details. We have nitrogen gas, which exists as N2. So we calculate the molar mass for N2, which is 28 grams per mole. Then we convert our 290-gram sample into moles, and finally, we multiply by Avogadro's number to get the total number of N2 molecules.
So, after all those numbers and formulas, what's the real point? Well, understanding the mole isn't just about getting through chemistry class. It's about getting a genuine chemistry superpower. This quote just nails it. The mole is the link. It's the critical connection between the invisible dance of atoms and the world that we can actually see and touch and measure. Without it, modern chemistry would literally grind to a halt.
So really, the next time you see the word mole, don't just think of it as some random unit. Think of it as a key. It's the key that unlocks the atomic world, that lets scientists count by weighing, predict reactions, and actually build our world from the ground up.
In the end, the mole is this amazing bridge that lets us understand a reality we can't see. And it kind of makes you wonder, doesn't it? What other bridges are out there in science? What other formulas or tools or ideas help us make sense of the parts of our universe that are hidden just out of sight? That's something to think about. Thanks for tuning in.